Okay, so it's still Wednesday, whatever that is, the 15th I think. So this is now the continuation of topic 10. We finished earlier just talking about potential energy. So the formula we had for potential energy, gravitational one, negative GMM on R. The gravitational potential energy will always be negative because it is defined as zero at infinite separation, and the two masses will fall together and lose potential energy, so it must be negative at any finite separation. Important point. For electrical, again, it's defined as zero at infinite separation. The two charges, if they are opposite, will fall together just like two masses, and so the potential energy will be negative. But if the two charges are positive, then you've got to do work to bring them together so the potential energy will be positive. Hence the plus or minus KQQ on R, but the same format, GMM on R, KQQ on R. In terms of a definition, and this is quite a common question as well, gravitational potential energy is the work done in bringing a small point mass from infinity to that point, and that will be negative. For electrical, the work done in bringing a small point charge from infinity to that point. That could be positive or it could be negative, okay, depending on which one you're bringing, whether you're bringing a positive towards a positive or a positive towards a negative, and so on. Okay, potential is not the same as potential energy. They are different things. Gravitational potential, sometimes that symbol phi, the Greek letter phi, or VG. V for potential, and for electrical we've got VE. So V gravitational or V electrical. Potential is defined as the potential energy per unit mass. So that's GMM on R, negative GMM on R, divided by N, the little n's cancel out. So gravitational potential is negative GM on R. The units from here, so I've put boxes around both of those formulas. That's an important one, and also therefore potential energy is just equal to M times Vg. Right? And delta EP would be M times delta Vg. If you go from one point to a point of different potential, then the potential energy will change. And how much will it change? Well, multiplied by mass, depends how much you move from one point to the other. From this one here, the units of V will be units of EP over the units of mass, so joules per kilogram. Joules per kilogram are the units of potential. Electrical potential, same thing. It's defined as the potential energy per unit charge. Again, KQ on R divided by Q, the Q's cancel out, so we're left with plus or minus KQ on R, where the units of this one now are joules per coulomb. Alright? So from here, potential is energy per charge. So electrical potential is joules per coulomb. And potential energy is Q times V, or delta EP is Q times delta V. So in some ways the most important formula there is that EP is Q times delta V. And of course that's where the definition of the electron volt came from. So if you remember the direction of the electron volt, it's the amount of energy gained or lost by an electron when accelerated by a potential difference of 1 volt. It comes from here. EP is equal to Q times V, or Q times delta V. If you've got 1 volt, so the unit of electrical potential is joules per kilogram per coulomb, or volts. And not many quantities where the symbol is the same as, so V potential is measured in V volts, which could be a bit confusing perhaps. So an electron volt is the amount of energy gained. It's 1.6 by 10 to the minus 19 times 1. So 1 electron volt of 1.6 by 10 to the minus 19 joules. Okay, defining both of those then. And again, these are quite common questions, so you need to have these definitions, somewhere in your memory. Gravitational potential is potential energy per mass. Therefore, it's really just this per unit mass. Gravitational potential is the work done per unit mass. Per mass. In bringing a small point mass from infinity to that point. Okay, that's a 2-mark question. And electric potential, same thing. Electric potential is the work done per unit charge in bringing a small point positive charge. Clearly, you know, it doesn't matter with the mass, but it does with this, because if you're bringing a positive charge in towards another positive one, then the potential will be positive. If you're bringing a positive charge in towards a negative charge here, then the potential will be negative. So we need to throw that bit in as well, and that's probably the more likely one, where you're getting 1 mark per unit charge and another mark for saying it's a positive point charge that you're bringing in. Okay. Alright, so the whole concept, so let's put together all those formulas then. So you've got grav and electrical. The pen that works in blue on top. Okay, so the force, I'll put that in the middle, force, F equals G M on R squared. F equals K Q on R squared. I guess we're measuring it in newtons, we're measuring it in newtons. The field. G equals F over M equals G M on R squared. Let's bring that in a little bit so I've got room for the units. G equals F on M equals that. The units will be Newton per kilogram. And for electric field, E for electric field is F over Q. So we've got KQ on R squared, that's measured in newtons per coulomb. I'll put in here also volts per metre. That comes into it later on. Potential energy. EP is the integral of F dr. I'll start with the gravitational. EP is the integral of F dr equals negative G M on R. That's measured in joules. The integral of F dr is plus or minus K Q on R. That's measured in joules as well, of course. And finally, potential. V gravitational is equal to EP over M equals negative GM on R. That's measured in joules per kilogram. And electrical, you've got that VE, the electrical potential, is equal to EP over Q, gives us plus or minus KQ on R, and that's measured in joules per coulomb. So you've got that really nice set of formulas. I'll put this line down the middle. There. So one side gravitational, the other side electrical, and they are so similar. They're the same format the whole time. All of this is in your data booklet. But in many ways it's the linking bits as well. So E equals F on Q, so F equals QE. G equals F on M, so F equals MG. You knew that one anyway. And similarly with this one, gravitational potential is EP on M, so potential energy is M times the potential. And the electrical one, EP equals Q times V. Okay. Equipotentials. Equipotentials? Well, equal potential. So Now, as you move away from the Earth, the potential, gravitational potential, is negative Gm on R. So that means that at a given radius, the potential will be a certain amount. So let's draw the Earth again and draw in the potential line. So this would be V1, this would be V2, this would be V3. So so each of these lines, so that V1 is all the same distance from the Earth, V2 is a different distance, V3 is a different distance from the Earth, but all of those have the same potential. So they're equipotential lines, well they're actually equipotential surfaces, because that would be a spherical shape. The Earth is spherical, and so any point that's 1,000 kilometres above the surface of the Earth would have the same potential. So they're actually spherical surfaces. So they're equipotential lines or surfaces. Note that if I was to draw in the field is looking like this. I don't know why I start with that one, but if you draw in the field lines, make sure you go all the way to the surface. I remember one year where they took marks off the field lines not going all the way and touching the planet, which I thought was a bit fussy. All right. What can you tell me about the relationship between the gravitational field lines and the equipotential surfaces? Well, hopefully you can see that they're perpendicular at all points. So that becomes a significant point. Let's look at this. So, for example, if I had two charges, so that's true. So perpendicular, the field lines are always perpendicular to the equipotential surfaces. As we went out here, let's say that was, I'm not sure if I've drawn them here roughly, so let's say that was, say, 10 centimetres, 20 centimetres, 30 centimetres, for example. We know that the potential is proportional, so they would be negative. As we got further out, it might be that, as we went further out, we'd be getting closer to infinity, so the potential would be zero out here. It's getting more and more negative. So if we were told, for example, that here was negative 100 volts, for example, all right, we could work out the others. I'm assuming this is 10 centimetres, 20 centimetres, 30 centimetres, or 10, 20, 30 somethings. So this one is half the distance, therefore twice, so that would be negative 200 volts. This one is 1.5 times the distance, so 2/3 as much, so that would be negative 67 volts. Or I could compare it with this one and say that's 10, 20, 30, so it's 3 times as far, so 1/3 as much. 1/3 of negative 200 is negative 67. So yeah, they could want you to make some numbers on there. The direction of the electric field. Okay, so the potential, so the gravitational field in this case, the gravitational field. The potential is going, is increasing in that direction. So we could say the potential gradient is in this direction, but the electric field is in, the gravitational field is in that direction. So the direction of the field will be in the opposite direction to the potential gradient, and I'll put that up in a moment as well. True for gravitation or electric field, gravitational, I suppose. Let's have a look at a more complex example where I've say got 2 charges. I'm going to have a positive charge and a smaller negative charge. The electric field between them. So I can draw the electric field lines. I know it's away from positive and towards negative. Alright? And so if I just had the positive charge, the electric field would be away from that. But the negative, it's just going to be towards that. So the overall electric field will be a combination of those. So we're going to end up with, out like this, and then coming in, out like that, and being bent around like that, out like that, and coming around, out like that, and coming around, and symmetrical the other side. That basically looks like 2 equal charges there. I'll make them 2 equal charges. So that looks nice and symmetrical there, away from positive towards negative, something like that, something like that, something like that, something like that. Alright? So what we've got here is the electric field. If I want to draw in the equipotential surfaces, then they'll always be perpendicular. So there's an equipotential surface coming down there. It's perpendicular to the field lines. There'll be one coming across like this, one coming across like this. It doesn't quite look perpendicular, but if I drew that around, perhaps it's coming around more sharply. And one like this, like coming around like this, coming around like that. And I'm trying to hit, cross those. The field lines perpendicularly, and not such a great one there. That should perhaps come around more. Maybe my field lines aren't particularly accurate, but that's a reasonable drawing. So in terms of the actual values of those, we know that the potential, as we approach a positive charge, will be positive. The potential around a negative charge would be negative. So I reckon I've got 0 volts here, and that might be plus 10 volts and plus 20 volts or something, minus 10 volts and minus 20 volts, something like that. And we could, it starts to be a bit tricky to work them out overall, but that would seem to be a reasonable sort of set of numbers for those. Okay, so what I haven't said is about potential gradient. So that's what we've got here. So I've said here that the direction of the field, the gravitational field or the electric field, is in the opposite direction, the direction of increasing potential. So the field is the negative potential gradient. And that's an expression that's used quite a bit. So the gravitational field is negative, the change in gravitational potential over the distance. Electric field is negative, the change in electric potential over distance, and this one becomes significant shortly. Hence, the units for gravitational field could be the joules per kilogram per metre, or in this one, this could be volts per metre, and that was what I threw in on the diagram earlier. In this one here, so the potential as we go across the middle line here, we're going from negative 20 to negative 10 to 0 to 10 to 10 then to 20. So the potential is increasing in that direction. That's the direction of the potential gradient. So that becomes the direction of the electric field in the opposite direction to the potential gradient. But numerically that works out as well. If I've got 10 volts and 30 volts, and there's 5 centimetres, then the E field is equal to negative delta V electrical over delta X. So I've changed by 20 volts from 30 to 20, so it's 20 volts over 5 centimetres, 0.05. That gives me, what, 400 volts per metre. So that would be the electric field. The direction of the electric field, we're increasing voltage in that, the potential in that direction, voltage or potential. That's the direction of increasing potential, so that's the direction of the electric field. Last bit here. Okay, so parallel plates, and they get used a lot in a whole range of electrical situations, particularly accelerating electrons. So in older style televisions, I mean, things have changed a bit now with LED and LCD, but in the older ones, you had parallel plates, which would accelerate electrons across, and would also bend the path of electrons. So in this situation here, I've got a battery here, and that's clearly the positive side of the battery, and that's the negative side. So what we end up with is a whole lot of positive charges on this side of the plate, and a whole lot of negative charges building up on this side of the plate. That actually comes in later into capacitors. Effectively, that's acting as a capacitor, but that's not till topic 12, I think. Okay, so the electric field is going to be between the two, away from positive and towards negative. And what we get is a very uniform one. So straight across, And so I'm going to draw these lines here, and I'm going to make sure, firstly, that they are touching both plates and that they are spread out evenly. Remember that how close the field lines are is an indication of how strong the field is. If I'm saying this field is constant and uniform, it's a bit more spread out, but it's, it's not too bad. Okay, so they're pretty even. And then also what we want is that at the edge here, the field's going to be weaker, so therefore the lines are going to spread out more. So we've got that there, it's often called the edge effect. Alright, so, often they'll ask you to do that, and sometimes that can be a 3-mark question. Alright, so you need to work out which way the field lines are going. Clearly they are going from positive to negative. So the top plate may or may not be positive, it depends how they've got this connected up. But I've got those lines spaced evenly. I've got the arrows going in the right direction from positive to negative, that's 2 marks, and then another mark for it bowing out at the end. So the field lines are a certain distance apart, maybe that one's not shown too well. Let's just give ourselves a bit more room here, where we extend that a bit. That was distance D. And so the field lines are a certain distance apart, but they're further apart here and further apart here, so that means the field's weaker. Alright? So note the field lines are equally spaced. Positive to negative, and then out at the edges, weaker field, edge effect or end effect, and the magnitude magnitude of the electric field is given by E equals V over D. Alright? So the electric field, of course, gets stronger if you've got more voltage, and the electric field gets stronger if you put those plates closer and closer together. And so often what we're going to have is an electron flying through the middle here, and an electron would get bent upwards, attracted by the positive one. A neutron going straight through, and a proton being bent down, an alpha particle, a positive alpha particle bent down as well. So parallel plates become fairly significant in that, and so there's the electric field, so therefore the force on a charged particle, F is equal to Q times E from our formulas. I've already got that out now. Electric field is F over Q, the force per unit charge, therefore F equals QE, so F equals Q times V over D. Acceleration equals F over M equals Q V over M D, etc. So an electron going through would be deflected by that. And perfect timing, Jim, because I'm just about to finish.